Hello and welcome to the third video of Intro to R in RStudio. In this video, we're going to talk about when to run a scatter plot, run a correlation, run a simple ordinary least squared or OLS linear regression, run a multiple OLS regression, so multiple variables, one dependent variable. We're going to run and assess multicollinearity and run a commonality analysis, one of my favorites. I'm going to show you how to export results out of RStudio onto your local machine, as well as how to export APA formatted tables into Word. So let me go ahead and close out of this. So what we're going to do now is we're going to look at the relationship between continuous variables first. So we're going to try to determine the relationship between GDPPC and corruption, leaving corruption on its original scale of 0 to 10. The most basic graph for two continuous variables is a scatter plot. The scatter plot will show that the two variables appear to be related. Will follow us with a visual inspection with two tests. First, a correlation test to see how tight that relationship is between the two variables. As a correlation close to 0 means there's no relationship. A correlation close to 1 or -1 indicates a relationship very close to a perfect straight line. Second, when you run a regression to tell us the nature of that line in question. A line is defined as the slope and an intercept, or y equals mx plus b, or rise over run. The regression output will tell you if either of those is statistically significantly different than 0. So for a correlation, that's the measure of association between two variables. The sign indicates an inverse direction versus directly proportional relationship. So 0 would be non-relationship, while a value of 1 is a perfect positive relationship, and a -1 is a perfect inverse relationship or perfect negative relationship. So what we're going to do is we're going to go ahead and we'll skip on a little bit. Actually, let's just first run scatter plot. So we're going to say plot our corruption 2. That's our x variable. We're going to have our y variable. Now we're going to have main, which is going to be our gross product. So that's our main figure title. And we're going to add labels for our y and our x. So here is our relationship here. So yeah, that looks roughly linear. Let me go ahead and just adjust this. And we can see a little bit of a floor effect here. So it's as low as it can get for GDPPC. And there's a couple of outliers here, like, okay, what might be going on there? I'm going to go ahead and add a line of best fit, or an align here. So I'm going to go ahead and superimpose a line within there that's going to try to minimize the residuals or the errors within that. So we're saying align when a linear model, and it's going to be GDPPC regressed on corruption 2, or that's y regressed on x. We're going to say make that line red, and we're going to change the size and length of it. So there we go. That's our line of best fit from our regression. And it looks like it's a negative relationship. So as corruption increases, GDPPC reduces. Now, we're not making any causal arguments with this because this is cross-sectional data. We would need longitudinal data to make causal claims within this. So looking at this, we're also going to go ahead and do a quick thing from the correlation package. We're going to run correlation on our CS. This is going to run all combinations. Let me go ahead and just change this over a little bit so it's easier to read. So it's corruption for every single variable. Corruption with GDPPC. What's the correlation? Our upper and lower bounds for confidence intervals, our t statistic, our degrees of freedom, and our p-value. So this is a quick way to do this. If you rather than a correlational matrix, where it gives you the statistical values that you need to report as well. There's a lot there, but it works out pretty well. So let me go ahead and move this over a little bit. Okay, so another way you can do this too is we can go ahead and run just a simple correlation between GDPPC and corruption 2. We're going to use complete observation. So if they have no missing data for either of those, use those data. So they have to have both values. And because these are two continuous variables, we're going to use a Pearson correlation coefficient rather than like Spearman, point by serial, or some other variations. So I'm going to go ahead and run those. Okay, so don't have to worry too much about that. So let me go ahead and just run that. There we go. I think I had something else highlighted before. Yeah, okay. But there's our correlation, -0.89. If we scroll up between corrupt GDP PC and corruption 2, -0.89, it's the same thing. I like this one above here because it gives us the upper and lower bound. It gives us the degrees of freedom, the and some other information in there too, the t and the p-value. So I like that better. But we can then also use a core test. This is just a simple correlation, but if we wanted this statistical significance, we would just add the dot test to this function. And now we get the same thing here. We have the t, degrees of freedom, the p-value, the upper and lower 95% confidence interval of that. Same information as we got above, but just a little bit more compressed. Great. Um, so now that we have that, we can then run a regression. So regression allows information about the relationship of the two variables. Specifically, it allows you to guess the value of one variable given the information about another. So we're going to regress GDPPC, our dependent variable, or on corruption 2. That's our independent variable. So first thing we need to do is we need to write a model and save that as an object. So we're saying run a linear model. We're going to say what our y variable, or outcome our y is. We're regressing that, so that's the tilde on corruption 2. And we're saving those results as model 1. We can then do summary model 1, and we can see what the output is. So we have our residuals, the minimum, maximum, median, first and third quartile residuals. We can look down our coefficients. We get our estimate, our intercept. And then for each unit increase in corruption 2, there's a 4,762 reduction in GDPPC. And both of these are statistically significantly different than 0, since they're both p less than 0.050. We can also then, so yes, there are significant differences. We can then put this as a equation, so we can do GDPC equals our intercept plus, or minus actually, 4,762 x1. So we can kind of plug and play that and predict. We can also add additional independent variables by adding just a plus symbol here. So we can go ahead and put OCD member in there. We can run that. The nice thing here is because this is a dummy coded variable that we factorized, it's going to say going from no to yes, because no is our reference group. Being an OCD member increased GDPPC by 8,153. And that is statistically significant, holding all corruption 2 constant, or controlling for corruption 2. We could also say that for each unit increase in corruption 2, there was a 3,716 decrease in GDPPC, holding OECD membership constant or controlling for OECD membership. We can then also run some regression diagnostics. So we can do our plot here. Oops, did not want that. And we can look at our residuals versus fitted, our QQ, our plots, and look for any potential outliers for leverage in there as well. That's great. We can also do things like, I'm going to go ahead and look at performance, which is a nice way for assessments of regression models. So we can go ahead and do something like a check. No, let me go ahead and do performance, 2:. Let's check collinearity of model 2. So when this happens, because I used one way of doing this, it's going to go ahead and give this warning message. So what you can then do is we can actually change this. This is a different way of doing it. It's going to be the same idea though. Data equals CS. Same exact results. Nothing's changed. There's our VIF. And if we did, let me scroll up a little bit. Same information, just gives you a little bit of a warning message. I like using $sign or object $sign variable name. That's what I'm used to. You can use this as well. But we can use like the performance packets to check, do regression checks here. So if I do check, say I want to check model, and I'll put model 2 here. The nice thing is it's going to give us a nice little bit of information here. We're just going to give it a second. If you don't have performance installed, go ahead and install it first. I already had it previously installed, so it's not a big issue. Um, that's weird. Um, it's not loading it in right. Okay, let me try one more time. Sometimes you have to change over the sizing of it. Okay, that is super weird. So sometimes when that happens, what you might need to do is you might need to find this and go ahead and then uninstall and then reinstall it and then try doing that. For time, I'm not going to try doing that. That's weird. R does some things every now and then. But we can go ahead and do the check model that gives you a bunch of different things for the model. So it's in a quicker format rather than everything. But I'll go ahead and just reinstall that. That's going to bother me. And I'm going to go ahead and do that. All right, so when you have multicollinearity, let's say that we had our VIF here. I'm going to wait for this to finish loading. Hmm, that's weird. You know, here, you can also kind of just do like check model. Let's say I want to look at heteroscedasticity. This is probably just the easiest way. Model 2. Yeah, so non-constant error variance. So we'd probably want to fix that. Use maybe a robust estimator. Okay, so I'm just going to clear this output here. That's going to bother me about the performance. I'm going to have to look into that. But let's say that we did have some multicollinearity. What I like to look at is commonality coefficients. That lets me know how much is shared in unique variances in the model. So what's unique to corruption 2 and OCD and what is shared amongst the variables? So think of it as like a Venn diagram. Oh, let me go ahead and do, I know what I did. Library y hat. There we go. So by using the y hat, so we're going to get the variance. So of the R squared, how much is unique to corruption 2? How much is unique to corruption 2? What's common? And what's our total? So our total is 83% of our R squared. Well, how much is in common to it? Well, 54%. So there's a big overlap between our Venn diagram here. We can kind of look at, well, what's unique and common. So I really like this. We can also use regr function. And then this is going to give you a bunch of information. So again, I'm an experimental psychologist by training. My stats background is in educational psychology. So what I like to do is I like to interpret beta weights or standardized coefficients. This gives it to you. So it gives our corruption category and our dummy coded standardized beta weights for our two variables. We also get structure coefficients, which is the correlation of the predictor with our synthetic y variable or our y hat. What's our predicted value? When you have that and you square that, that's your squared structure coefficient. So how much it could have accounted for of the outcome variable. So if you have multicollinearity, this is Corville and Thompson, 2001. Yeah, I think it's pretty Corville and Thompson, I believe, 2001. If you interpret beta weights and structure coefficients, you don't have to worry about multicollinearity. So that's what I do. We have our commonality coefficients that we ran before. We also have our effect sizes and different variations based on this. We can then take this, we can take our coefficients and we can write this out to a CSV file. So we're going to say write CSV. We're going to take our model 2 coefficients. So for model 2 summary, we're just extracting the coefficients here. turning that to a data frame here. So we're nesting the functions and then writing that data frame to something called Model 2 CSV. We can also do the same thing with our OECD corruption table. And if we do that, let me open up a little explorer here. And now we have our Model 2 here. So I'm going to go ahead and open this one up. It'll just take a second. Here are our model coefficients. So our estimate, standard error t, and our p-values for our regression. We can also open up our table that we created for our proportions here. So whether or not they're an OECD member and our 3 levels of corruption categorized. We can also write this out in terms of an APA table for our mean standard deviation correlations. So we have, before we installed and activated our APA tables, so what we're going to do now is we're going to go ahead and say APA tables. We're taking our CS data frame. We're going to say file name is descriptive statistics table 1. We want the confidence intervals, and this is going to be landscape. Because I had to restart, I'm going to go back up to my library, and I'm just going to go ahead and rerun everything there. That's going to go ahead. So if it restarts on you, this might happen. Just go ahead and rerun it, and you're fine. I'm going to go ahead and run that. So it prints out here, sort of our descriptive statistics. I'm going to go back to my working directory, and let's see, there's our descriptives doc. Let's go ahead and open that one up. And it's not in perfect APA format, but it's pretty close. So we can go ahead and we have our means, our standard deviation, and then our correlations matrix here. And we would go ahead and we can correct this, put it more into APA format. It's pretty close. We can also take our regression table and say we want model 2. And we're going to put number 2 for the table. And we want the 95% confidence intervals here. I'm going to go ahead and run that. And there's our regression, model 2. And so now we have our table 2. We would change the title a little bit. And we can go ahead here. We have our semi-partial correlation squared. Essentially, you can interpret this as unique variance accounted for by that predictor. I like using commonality and beta weights personally, but to each their own. But it's pretty close to APA format. We want to maybe change a couple of things here, but it saves you some time and energy. So once we're all set, we can go ahead and close out. So I'm not saving anything here, but let's say we wanted to save RDS. Let's say I wanted to save our formatted data set. I could write CS cleaned dot RDS. If I run that and I open up the window again, going to go in here. And now we have the clean format here, so I can go ahead and clear this out. And if I wanted to read see load. I'm trying to do this from memory. So this is CS read RDS, and I'm type in CS. Now, if we do this, it's going to go ahead, it's going to pull the RDS using that function. We're going to assign it uppercase CS. There's our data set here. And the nice thing, if we expand this, has our new variable we put in there, and it keeps the ordered and the factors that we had to add all that. If we don't do that, we have to redo it. But I'm going to go ahead and save this, and I'm going to go ahead and close out of this. And go ahead and just don't save because you can just rerun everything. Well, this concludes the introduction to how to work with R&R Studio for intro. One thing I do want to mention at the bottom of the PDF, there is a link here to R for Data Science. It is a fantastic, this is second edition. It's a fantastic open source book that teaches you all different things about R. and has some different ways of doing things. Highly recommend it, and it's a great starting point. Well, I hope this was helpful, and thank you for watching.